Hello, everyone. We're the end-to-end model probing team, and my name is Sue Park. I'll be kicking off our final presentation. So as a quick introduction, think of a scenario where a child is first learning a language. They'll most likely start with picking up a few words from their parents or their caregivers, and maybe they'll immediately start saying like a very simple sentence or two. But will they also be able to read long passages and identify the author's assumptions to draw high-level conclusions? Well, this sounds much more unlikely. And if this is like far from plausible, what specific knowledge would the child actually need beyond some vocabulary and simple syntax? This little snippet was to introduce you to the topic of model probing, where instead of a child, a language model learns to solve different language-related tasks. So model probing is a method for examining whether certain linguistic competencies, such as basic syntax and semantic roles, are in large language models, such as BERT. And in the currently existing probing paradigm, there is a disconnect between the probing tasks and trained classifiers, and the linguistic competency used by the models in downstream tasks remains uncertain. For instance, let's say there are two sentences. First, he ate salad with a fork, and he ate salad with a dressing. We want to know if the model is grasping the intrinsic semantic differences between a fork and a dressing, and is able to tell whether he had also eaten the fork or the dressing along with the salad. In this project, we will attempt to develop a theoretical and empirical framework for end-to-end model probing, where we probe models for the ability to capture certain linguistic phenomena, building on the recently developed methods for interpretable evaluation, such as the explainer board and checklist. Our goal is to enhance their interpretability, interactivity, and reliability of software systems for natural language models for researchers to understand how and why a system is working, where it is failing, and how to optimize. We aim to develop a tool that inspects system outputs, identifies the strengths and weaknesses, and inspires the users with suggestions on specific linguistic competencies to tackle for improved performance. Our proposed product and solution includes a research publication, a GitHub repository, and an open source platform like the explainer board. It's two parts, first being the sandbox implementation we have completed in the spring semester, where we try to understand whether a model's embeddings contain a certain linguistic tendency. We reproduce the results of a BERT-based research by collecting and converting datasets into a unified representation based on span relation representations using the GLAD benchmark, and predicted over these spans, then utilize the explainer board to conduct a systematic analysis of the outputs across different tasks. This semester was dedicated to end-to-end implementation, where we tried to understand whether a model uses a certain linguistic tendency for a task. We constructed end-to-end probing datasets with pseudo-labels on end tasks, implemented a training and evaluation framework for end-to-end probing, visualized the results and gleaned insights using the explainer board's existing web interface, and lastly, conducted system-level and case-level analyses to investigate correlations between the probing tasks and the end tasks. We have three major scientific hypotheses. First is that there are non-trivial correlations between probing tasks and end tasks. Second, that different end tasks focus on different linguistic abilities. So certain linguistic properties encoded in the language models trained on simpler tasks, which we call probing tasks, are crucial for solving more complex tasks that require syntactic and semantic information, which results in meaningful correlations between edge probing results for those two types of tasks. And lastly, that end-to-end probing can help deductively diagnose the causes of errors in the end task by attributing to success or failure of probing and end tasks. There are two major key features to our project. The first, it is an end-to-end model probing framework that is a unified interface for a customized, automatic, and end-to-end evaluation on various linguistic properties and natural language understanding tasks for any model. And also that it is an open source framework library that is compatible with mainstream network architectures and deep learning frameworks. Second, that we provide a categorized model probing data set by building a benchmark data set covering multiple linguistic properties. And we've also created test cases for each specific language competency to evaluate the strengths and weaknesses of the encoders. Our main intended users are research scientists or research engineers working with ML or NLP systems to help them diagnose the strengths and weaknesses of a single system, interpret the relationship between multiple systems, and examine their prediction results. As mentioned in the first few slides, our system functionality is two-phased. First, sandbox implementation, and second, end-to-end implementation. Here is a more detailed diagram of the sandbox implementation, where you can see that we reproduce the results of BERT-based research by prepping the data sets, collecting and converting them to the unified representation, then using methods such as the Hugging Face predict over these spans and relations, then utilize the explainer board to. And second, here's another diagram, a more detailed breakdown of the end-to-end model probing part, where once the first phase is completed, we conduct implementation, where we conceptualize to connect sandbox and end-to-end and decide on the underlying tasks, retrieve data instances, and test out-of-domain robustness. Our non-functional requirements include a list of 6 items: usability, availability, interoperability, modifiability, performance and testability, and security. Our research requirements include data sets that we can use to evaluate the linguistic competencies of the language models, and pre-trained models such as BERT and Roberta from Hugging Face, and of course the computational resources with at least 32 gigabytes of memory. So with that, I'll hand it off to Ashley.
Okay, thanks, Sue. So I will be talking about end-to-end model probing deeper. So this semester, we designed end-to-end model probings based on a major limitation of previous work. So in previous work, they only use out-of-domain data. So for example, TNA in 2019 discovered the traditional NLP pipelines for question answerings by probing the onto-node data set, which is a very different data set, and then showed that embeddings contain a certain linguistic tendencies based on the onto-nodes data sets. But there is actually no empirical studies on whether a certain linguistic properties found by the probe was actually utilized in the end task. So we propose end-to-end model probing, which probes models using in-domain data as probing data set by generating pseudo labels of end task as probing data set. So here, for probing data set, it means like basic fundamental operations in natural language processing, such as product split tagging and name entity recognitions. And for end task, we refer to tasks that involve more complex operations that might utilize information from probing tasks. So probing task here, contains 4 different probing tasks in our design. So first category is span-oriented task, including NER, which is name entity recognition, and POS taggings. So you can see that there is only 1 span for each of the labels. And another category is relation-oriented task, which including semantic role labeling and dependency parsing that involving 2 spans for a labels, which is relationships, to make the predictions. And for end task here, we use glue benchmark, including 9 data sets. Like it contains acceptability, sentiment, and also similarity and paraphrase task, and also 4 different inference tasks. So here is a diagram that contains both data and model design of our pipelines. So first, we can see that this is an examples from COLA data sets that the example is ident the book to Tony, and it is separated by token. So each of the input tokens will be input to our probing task taggers, which is POS, NER, dependency, and SRL, semantic role labeling taggers that we get from the open source that is actually have a SOTA performance. And after going through the POS going through the probing task taggers, we will get multiple pseudo labels for one sentence. So these examples for POS tagger, we get 6 labels for this one input sentence from the end task. After we get the pseudo labels, we will try to probe these pseudo labels using edge probing, which we freeze the pre-trained encoder like BERT or Roberta, and then get the span representations for each of the tokens. And in these examples, I took the 0 to 1, which is this I labels, and then go through the classifiers to predict these correct labels. And we do the same things for all 4 probing tasks. So each of the classifier is dedicated to each of the probing tasks. And after we predict the probing labels, we will need to aggregate the metrics for end test instance, because like I talked about, for each of the sentence, we might have multiple pseudo labels. So we need to aggregate them for each of the instance. And also we will have to aggregate all the instance level metrics again to form a system level matrix. And this is for our probing pipelines. And as for the end task pipeline, we can see there's another line connected to this pre-trained encoder. So this pre-trained encoder is actually not freezed because we need to fine tune it. So after going through this pre-trained encoder, we get the sentence representations of this sentence, and then go through another classifier to get the COLA labels. And it would be 1 labels per sentence. So this, we will have a system level metrics for COLA. And for the probing task taggers, we select POS tagger and NER tagger from Flare, and dependency parsing taggers from Stanford NLP, and SR taggers from Allen NLP. And our experiment design involving 2 models, which is BERT and Roberta, and layers, which is 12 layers. So each of the layers, we will extract the representation from each of the layers to do the probing and end task predictions. And probing task, we have 4, and end task, we have 9 from GLUE dataset. So the total different experiments that we need would be 2 times 12 times 5 times 9. So we actually have trained 1,080 models. And for test designs for probe the dataset, we use edge probing. That is a multi-level classifier over spans. Because we have multiple spans, we just use the span representations inside it to do the classifications. And probing classifier, so we freeze the pre-trained encoder like I talked about before, and common matrix including precision recall F1 and correlations for different kinds of tasks. Next, I will hand over to Divisha for our system and design overview.
So our system architecture consists of 4 major components, those being the probing dataset manager, a model probing module, and an external module for explainer board. So our probing dataset manager manages all of the probing datasets and provides a unified data loading interface for all the generated probing tasks. Our model manager stores and loads parameters of different language models that Ashley mentioned. And the model probing module conducts all of the probing tasks and performs extensive evaluation to provide metrics for our explainer board visualization. And finally, using explainer board, you can interact with the system and redirect probing requests to the backend service and interactively visualize results on the website. So one of the major tools or dependencies that we have used in our project is Explainer Board, which is an open source system maintained with GitHub and currently deployed as a web toolkit. So users can either use the command line interface to prepare, train, and evaluate the model through the CLI, Or users can also use the SDK version to call different functions using their Python code to get the object result or upload their probing result to the explainer board system. Finally, users can also use the explainer board UI to which provides comparison and visualization of the metrics on the UI itself. Our deployment model consists of a standalone Python package where we provide probing dataset preprocessing modules and training and analyzing modules in an end-to-end or a decompositional manner. Users can use this package to perform model probing on their own models. So firstly, here users can perform end-to-end probing where using BERT and specify the model directly, tasks, and data sets. Users can also use our data preprocessing module to prepare their own data sets and preprocess them into joint representations for the probing tasks. Finally, users can specify which probing tasks or probing data sets they would like to evaluate. So there are certain risks and challenges involved in our product, which we would like to address. Firstly, we have the business risk that the framework may have difficulty gaining market acceptance. So ideally, we want to disentangle the role of each dataset from the role of the original model and the classifier. However, in practice, models are trained with varying datasets. So statements about models tend to be confounded with the issues of the datasets. Secondly, we have the product risk. That is, if the probing result of our framework indicates strong linguistic properties learned by the target model, probes might still not be able to tell whether the data is causally related to the target model's behavior or not. So this might cause the researchers to head in the wrong direction by believing the result that we show. Finally, we have our project or process risk, where we hypothesize that there will be a non-trivial correlation between a model's performance in the sandbox probing task and its performance on end-to-end tasks. And if the results of these experiments contradict each other, it would require enormous effort to redesign our product. So as Ashley mentioned, we performed 1,080 experiments and to test the different hypotheses that we mentioned before. And we wanted to perform certain system and case level analysis to aggregate the results of the experiments and visualize them. So this will help us prove or disprove the hypotheses that we mentioned. So firstly, we do a system level analysis to prove the hypothesis, which is non-trivial correlations between the probing tasks and end tasks exist. So for this, we trained a linear regression model to predict the end task performance using the probing task performance as features. So after aggregating the results, we found that we were able to successfully predict the end task performance for 8 out of the 9 glue benchmarks. And for the one task that we were not able to accurately predict the performance, we hypothesized that this is because the data set itself is quite small, and which is why the trends in the graph are not clearly visible. I'll hand it over to Yunshin, who will go into further system and case level analysis.
Thanks, Divija. Yeah, so in order to prove our hypothesis, like there's non-trivial correlation between probing task and end task. Like we designed two probing paradigm. The first is sandbox probing. The second is end-to-end probing. For the sandbox probing data set, we use the static set of out-of-domain probing data, which we collect those like dependency parsing, SRL, NER, post-tagging data from Pantry Bank or semi-evil task. While for the end-to-end probing, we're using the SOTA model to generate the in-domain like low-level probing tasks on the fly. So the strengths of the end-to-end probing is we can not only perform the system level analysis, but the case level finer granularity analysis on each case of the end task. And after we conduct about over 1,000 experiments, we collect a bunch of performance score for each models on different pairs of end task and probing task. So using this data, we calculate the correlation matrix on both the sandbox and the end-to-end settings. And we can see they show very similar but slightly different trends in this correlation matrix, where for SSD2, the correlation of post-tagging, dependency parsing, and SRL to the end task is relatively high, while for on WNI, it shows relatively low correlation performance on both of the 4 data sets. And so this two correlation matrix can give us a higher level understanding about which low-level tasks the end task is more focusing on, and that's our system level analysis. After we got this high-level understanding, we're pretty much want to understand which what's the different concentration of the end task we can have from our probing. Like firstly, we designed this regression task as a logistic regression model to predict the true label using the performance as the features. And we got a baseline model over here. Like it only used the prediction labels of the our backbone models, well, plus 1 features at the time to analyze the performance difference, which is the indicator of how important these features are for the end task. So we can see after we add the post tagging features, the performance of predicting the true label on the end task increase. Well, the SST2 and MRPC shows the most significant improvement. For NER, the COLA, WNI, and RT and QQP shows significantly more higher performance improvement. And for the full model settings, we are using all the 4 features and predict the true labels of the end task. We can see there's around 20 to 40% of improvement on the prediction task. Well, it also we also did some ablation study to remove 1 feature at a time to see which one is more important in this full model settings. And so from this experiment, we know that different end tasks will target on different linguistics abilities. So, however, this experiment is still on a system, a higher level aggregated result. So next we can dive deeper into a specific case from our probing results. So here we sampled an error case from MRPC, where it's an error case that this data set is for the paraphrase classification, and SINT1 and SINT2 is actually equivalent. However, the model predict this sentence pairs as non-equivalent. So if we only have this wrong label without any deeper, finer grained analysis, we don't know what's wrong or what's going on for this model. But here is our probing results. We can see the post tagging accuracy is low, where the error case is the model classified in from a noun to a preposition, which is incorrect, and that also leads to the dependency parsing model failed, which the in backlit LCD screen should be a noun phrase, but it predicted as a adverbial phrase. So that leads to the failure of this this dev case. And the second case is from the QNLI dataset, where it's adapted from the squad QA data set. The question is in what city Marriott did the Panthers stay? The sentence is the Broncos practiced at Stanford University and stayed at the Santa Clara Marriott. So actually the sentence pair doesn't have an entailment relation because the question is asking for the Panthers, while the sentence only contains the information of Broncos. Basically, in the QA model settings, we only know we made a wrong prediction on this sentence pair. However, we might think that is because the models concentrate on the local syntax of state at the Santa Clara Marriott. So they might provide a Santa Clara as the correct answer. But actually, this is very counterintuitive when we are inspecting our probing results. Our NER accuracy is low because the model misclassified the Santa Clara Marriott from a location to organization, and that might be the reason why the model give the wrong prediction labels on this sentence pair. So this two case level analysis show how the end-to-end probing can help the machine learning engineers and researchers to get a fine-grained analysis on the error cases. And here's our future work. So firstly, we're currently applying our end-to-end probing to only the GRU benchmark, which is very simple classification and regression task. Next, we can apply this method to even higher level complex tasks like generation and machine translation. And also, the next step to provide after we get the weakness of the language models, we can generate some enhancement data by incorporating like the adversarial training cases in the pre-training phase to improve the specified language properties of a language model. Like thirdly, after we got this all performance scores of the different models, we know the weakness and strengths of these models. So when we are encountering a new task, we can use the performance score of the probing data sets to do the model recommendations, so that the ML engineers can get more flexible and pertinent advices on the bunch of existing language models. So yeah, that's basically what we have done for the 2 semesters, and thanks all our group mates and also Professor Graham Newbig. Yeah.
Hey, thanks guys. Great job on the presentation. I really enjoyed it. Did you have a slide near the beginning where you listed your hypotheses?
Oh, sure. This one?
Yeah, perfect. Okay. Yeah, so I think this is really interesting because for a long time, if you publish a paper like in question answering or IR or something, you have to talk about these correlations if you're using things like entity labels, as part of your solution, and you have to say sort of how good does the entity labeling have to be, and in order for your approach to work, right? So I think this is very valuable. I think for me, I'm not surprised that you found support for these hypotheses, because I think that entities are always an important feature. So there's always going to be some, kind of correlation between your ability to do entities and your ability to do any, downstream task. But I think there's other ways to expand this work, right? So you could take more of a language typology approach and then language developmental approach, and then think about evaluating on all the levels of the sophistication of the English language, grade 1, grade 2, grade 3, et cetera, and look at what linguistic structures are required for that. So I think that's a sort of there's an interesting implication here, which is that I believe that you can pick sort of probe labels and then downstream metrics, and then find this relationship that you've investigated here in a lot of different cases. And I think that maybe my question for you, and then I'll see if Graham has a question, is sort of if you could now use this to develop a really sophisticated model of a certain space, what do you think is the right space? Should you be looking at all the linguistic phenomena in the language, or should you be sticking to those levels that you've been looking at so far, which are common ones, but maybe larger grain size than particular grammatical levels, and then focus more on more task domains, more downstream stuff? So what do you guys think?
Yeah, I think as very beginning, I think we can definitely extend our probing task. Like currently, we only use the 4 like syntactic and very limited number of probing tasks now. But actually, the reason why an end task case is failed is may not only concentrate on this 4 tasks. So as you said, we can incorporate more like the language typology structured task as our probing candidate, and so that we can build a more more complex, more complete analysis system. Yeah.
What I like about this a lot is that you can imagine that if you were given the responsibility to model all of the data features in a particular domain, let's say it's bio question answering or something, right? You could end up with something like the bio ask competition, where you have entity recognition, as well as downstream tasks that you have to solve, and they're all interrelated. So the other thing I like about this work is that it kind of has us thinking about what are the most important core probing tasks that have the broadest applicability over the most downstream tasks, right? I think that's an interesting way of thinking about it.
Domain, like the beginning of last semester, we did talk about like the multilingual take on it. Perhaps
Okay.
that could be like a iteration too. Obviously, we focus on English, but the linguistic properties you mentioned, there are other languages that have their own unique set of features and unique set of phenomena. So
because
well, I'm thinking like if I have a company and I'm going to start developing NLP tools for lots of different business domains and different languages, it would be very interesting to consider what would be the balance between the tasks and also the maturity of the existing models or implementations. Graham, is there anything you'd like to ask the team? We have a couple minutes left.
Hi. No, not really. I've asked lots of questions, so yeah, good job. Sorry, it was a little bit late showing up to this, but nice presentation. I saw most of the end part of
Okay,
it.
so then maybe I'll just ask, what do you think? Are there any obvious weaknesses that the team should be working on with respect to what they've gathered as evidence for their hypotheses so far?
I mean, there's always more to do, but I think the one thing that could be a bit more satisfying is how much how much of a correlation we would be able to get between the the sandbox tasks or the linguistic tasks and the end tasks. That was harder than we thought for reasonable reasons, but I think overall we were able to find some interesting things, so not bad.
Well, yeah, maybe in the future, it's what a team could do would be to take one of those interlocking sets of tasks like BioAsk, where they're specifically engineered to be interlocking. And then I think you'd find fairly strong, evidence of the correlation, performance on the downstream task there. So that was a thought.
Yeah, I think that makes sense.
All right, guys, thanks very much. We got to move on to the next team. Thank you, Graham, again for all your time and mentoring the team.
Thank
Thank
you.
you, Graham. Thank you,
Yeah,
Eric.
thank you.